current AI tools where you can use to explain it. For example, if you copy the CMake file and try to learn it, it's pretty good, I think. And building Soar with the sconce files was like the major part to understand what sconce does and what like flags it sets to mimic the build structure and the build options, basically. After that, it went pretty good, actually. I was surprised how fast it got, or how fast I got it to work.
Okay, thank you.
No worries, you're welcome.
Well, thanks a lot, not only for your talk, but for all your service. It's great to have somebody contributing so much to the project. So thank you.
You're welcome.
All right, we're going to go to the next talk.
Hi, everyone. I'm Bob Wray, as I mentioned earlier, and what I'm going to be talking about for this talk is actually some work that was done by two students at the University of Michigan. Cindy Zhu is here with us today, and another student, Jason Lin. This is part of a thing that Michigan does called the CS undergraduate research program, and they actually pay undergraduates to do a 8-week internship with industry researchers to sort of learn about what the research process is like. So we talked about, what kind of problems they might be interested in. We went through a few different ones, and the one that they chose to work on was this question about reinforcement learning in SOAR. And in particular, SOAR's reinforcement learning was done 20-something years ago now, and it uses Q-learning. And Q-learning was the algorithm at the time. And Q-learning is fantastic in many ways, but it has a couple of limitations. One of the big limitations is that you have to enumerate all the states, which means that if you have a really large state space and you get a sort of combination, a very large number of entries in a table. And then the other thing from a SOAR perspective, we really like our agents to make decisions about the world that they're experiencing, but you have to decide as a developer when you have continuous values that you want to learn, a SOAR agent wants to learn over how to discretize that space, which is required for Q-learning. And so what we're sort of interested in this project is can we think about, there's lots of people that have sort of been thinking about in the last 20 years how to overcome the limitations of Q-learning. There's lots of continuous algorithms out there, most of them based on deep neural networks. And so the idea is that could we identify algorithms that might be better for our Soar-RL from sort of leveraging that research that's out there? So we had two key requirements. The first requirement is that we need to support this continuous and discrete state representation in SOAR. So we want to deal with continuous values, but we also know that every SOAR agent is probably going to have a lot of discrete values. And so we want to have a mix of both of those in one system. And there's also this issue with the distributed action reward representation, right? I can have a bunch of different productions from different places that are contributing to my notion of reward for a particular action. And then there's also some specific criteria that we'd really like to have for SOAR. Sample efficiency is really important. That's important for everybody, but it's really important for us because you can't assume that we can see thousands of examples before we can learn anything useful. We really want online incremental learning. That's sort of the way SOAR works, is that you experience the world, you get feedback, and you learn from that. And as we'll see, there's lots of reinforcement learning innovation that has happened that sort of breaks that assumption. And then we'd like to also have dynamic variable selection. Again, this is the notion of the agent making the decision, not a developer or a modeler making a decision about what's important. And so that means that we'd really like to have runtime decisions to what variables are important as opposed to making design time decisions. So that was some of the things that we were thinking about. We ended up taking two parallel paths. I'm going to talk about them in the inverse order in which they have, the reverse chronological order in which they happen. So one was just to take a look at what kind of methods are out there and characterize the learning performance of those methods. And the other one was to take a deep dive into one particular algorithm, this Deep Q Networks algorithm, DQN, and look at how we might implement SOAR requirements with that agent. We did all this in Gymnasium, which used to be called Gym when OpenAI sponsored it. Now it's an open source project in 3 different environments. these control environments might have ended up being not the right place for us to have looked, but that's what we did. We had a little bit of amount of time, so we chugged ahead. So I said that we wanted to mention these combinations of continuous and discrete values. We only looked at discrete outputs, so push the box left as opposed, there's also work on continuous outputs as well. We didn't look at that. We wanted this mix of discrete and continuous state variables. And so what we did was discretize some state variables in these control problems. So this is cart pole. You might have seen cart pole before, but you've got these 4 continuous variables, sort of the displacement from the center, x, as well as the first derivative of x, and then the displacement of the pole in radians and the derivative of that. And so what we could do is just say, well, I'm going to have the poles to the left and the carts to the left, and then I have some continuous variables of those functions as well. So that's kind of the way that we were thinking about formulating the problem. And then there's lots of variations that we looked at. So one is I can take, cart pole, I can easily take up to 4 discrete values just looking at that. And 8 variable instances for each of those. I can take the discrete variables as they exist, or I can manipulate them in some places. The obvious kind of manipulation here, if I have left and right, would be to take the absolute value of them. So that's what we did. And then I can also add random variables, and we're going to add random variables so that when we look at different domains with different number of variables, we can sort of kind of try to compare them. So I just wanted to mention this survey of RL methods. So what we did was we kind of wanted to say, how do these different algorithms, how sensitive they are to different numbers of variables? How do they scale? And so to do this, we relaxed some of our source specific requirements and looked at 3 algorithms. So we looked at PPO and actor critic. Those are both algorithms that sort of take this batch approach to learning, as well as a variation of DQN called double DQN. And we didn't really worry about this dynamic encoding of variables for this part of the project. So we just one-hot encoded all those discrete variables into a network to learn the network. And then, as I mentioned, we tried to standardize the variable space across the different environments. So what we expected to see was something like this chart. This is just something that we made up in advance, where the horizontal axis here is how many times do I need to see it? The vertical axis is some kind of notion of how much reward is accumulated. And kind of what we expected is if you have a few variables, you should get to the total reward pretty quickly. And if you have many variables, you can get to the total reward more slowly. And so that was our, sort of naive expectation going in. If we look at PPO on cart pole, again, the horizontal axis is how many time steps, how many episodes, and the vertical axis is the reward. Then for 2 variables, it learns pretty quickly. And as we add more of these variables, maybe there's a pattern there. But as we look further, this is a bit of an eye chart. You won't be able to see all the details, but we got PPO, A2C, and double DQN. And what you see is, A2C doesn't seem to learn a lot for any of these combinations, and maybe double DQN is learning, but it's learning pretty slowly, and the pattern isn't quite.
Faz uma semana que eu vou reorganizar algumas coisas. E aí eu vou te ligar, que eu vou realmente reorganizar.
Mute, please.
Entendeu?
Walter,
Esse lugar aí do projeto, é um lugar que eu quero
Fine. It's mute.
dar um up de tudo que eu aprendi nesses últimos 1 ano. Então eu preciso me reunir com você primeiro, colocar a estrutura e depois chamar o pessoal. Então você pode fazer isso, querido? Vamos fazer assim?
Sorry.
Don't play with it.
Ele falou, não, num grupo, pode falar. Quando eu acabei de conversar com o professor Walter, ele tem um novo, está pensando um novo no escopo, é isso. Ele pediu um tempinho a mais para poder colocar isso em estrutura. Você está entendendo? Tá, você fala isso e pede desculpas a eles por mim. Fala para você pedir desculpas, mas está acontecendo. Porque é o seguinte, deixa eu te explicar.
Could you please mute?
Tá aqui o John Laird está fazendo aquele seminário dele lá. Deixa eu coloquei aqui, pronto.
Thank you.
All right. And then if we look at the top row here is cart pole, bottom row here is lunar lander. These little circles just show you that the lunar lander has many more trials than the cart pole. What you see is it's not the pattern is not consistent over different domains either. So like we were hoping that, oh, just one algorithm's going to jump out. It'll be obvious that that's the algorithm. We only looked at a small number of algorithms, but even just simple changes moving from one domain to another. And this is important for the purposes of what we're trying to accomplish, is because we're not trying to solve cart pole. We're not trying to solve lunar lander. We'd like to embed an algorithm in SOAR that could be useful for whatever domain you put SOAR into. So it needs to be as flexible as possible, not specialized for a particular domain. So we also did this looking at deep Q networks, and this was the algorithm behind the Atari the Atari game player that was done by DeepMind, and it's a little bit older, but it turns out that this was like one of the early attempts to sort of deal with the problems of Q learning, and it really closely maps to Q learning. So this was very attractive to us because the idea is that, well, if it's very close to Q learning, then maybe the impedance matching, sort of being able to integrate this into SOAR would be a lot simpler. And basically the way DQN works is it captures a bunch of experiences in something called replay memory. And then it has two networks. The details of why it has two networks is not that important today, but basically there's a policy network that you're using to make decisions. And then every so often you update your target network, which is sort of your long-term commitment to here's what I've actually learned so far. And so this is what we explored, sort of went in a deep dive trying to think about how we would implement this in SOAR. This is kind of what we came up with, is that you have this replay memory. Each one of these functions that we're trying to approximate, we just have a policy and target net for each one of those. So you sample from the replay memory, you go to your policy net. I'm in a state that's left, so I'm going to go for left and decide which one I want to choose. So that was relatively straightforward to implement. It all seemed great until we tried to do learning, and then this is what we got. This is the horizontal axis, vertical axis of episodes. Horizontal axis here is reward. And what you see is that this happens to be a case where we ran it until we want to go 700 steps. So could you keep the cart going for 700 steps? And you see, it does pretty well for a while, falls off really quickly. This is not super surprising for DQN, and we'll talk about that a little bit on the next slide. And then, they did an amazing job of just kind of looking at every single possibility that they can think about exploring. And I'm not going to show you all those charts, but different exploitation strategies, different learning rates, looking at because that replay memory is a buffer and it's essentially a queue. Maybe there's some issues with memory size. We looked at all that stuff, and some of this changed, but basically it didn't work out. Here's some work. This is just basic cart pole, not cart pole with that the basic DQN. And one of the things that we see with basic DQN, this is now just 50 steps, but the same kind of pattern is happening here, where you learn something and then it kind of quickly falls off. And then we've explored this notion of learning rate scheduling, and especially looking at that diagram on the right, if basically we say stop learning once you reach a plateau, it essentially continues to learn. So you can't really see in that chart, but it goes up to 50 and pegs at 50, and we did it for 500. Again, I'm not going to show you all those charts. So if we hadn't run out of time, this might have been the direction that we would have gone in. In conclusion here, I think we have a little bit better understanding about state-of-the-art RL and how that maps to SOAR's requirements. It's possible that DQN or double DQN might work for us with a little bit more exploration. And then in terms of the call, just we didn't come up with like, wow, this is the algorithm for SOAR, which was ambitious, but that's where we hoped, but didn't quite get there. The other thing was just how inconsistent the different algorithms are over what seem like pretty similar domains. And then, as I mentioned, sort of the state of the art in RL has gone to these assumptions of batch mode. And so we really were looking at what can we do incrementally. And I wonder whether there's some compromise there that we can talk about. So I will stop there and then see if there's any questions, if there's time for any.
Thank you. First, we'll see if there's questions in the room. 3, 2, 1. Yeah.
So with this testing with the DQN and stuff, did you actually input the neural network like in Soar? Like, did you change the Soar C++ code, or did you call a Python thing with Soar?
No, this was all done. This was all us trying to understand how the behavior of the algorithms worked
Okay.
in a way that was informed by Soar, but we weren't trying to. We didn't do any kernel work here. Other than we ran. Well, yeah, we didn't do kernel work. We did do some agent work.
Okay.
So Jonathan has set the stage for us. He's raising his hand, and so I know I can call on him. So Jonathan, go for your question.
Thank you. Yeah, it's more just a flag that I think this is super interesting work, and I think it actually dovetails beautifully with the things that I want to talk about in about half an hour now. And in particular, the idea that replay is critical, but it has to be selective and it has to be similarity based in many of the ways that production systems work with regard to the matching to contents of working memory. And so I think there's a super interesting point of contact that I'm eager to hear what you think about what I have to say, and I'd love to talk more about it later.
Great.
Awesome. Thank you.
Okay, so if you have a question online, please raise your hand. Okay, we're going to thank Bob and the students.